I'm dividing my talk today into two different topics, starting with Gaussian processes in geology. So this section, looking at ways a range of different ways that me, along with some colleagues of mine, apply GPs to different types of geological data. So geophysical logs, geochemical logs, measure while drilling data, as well as a bit of surface modelling. The aim of this work was always to improve the understanding of the mine geology so the ore body was better understood. This then leads to improved scheduling and grade control. I completed this work at the Rio Tinto Centre for Mine Automation. So a Gaussian process can be defined as a collection of random variables which have a joint Gaussian distribution. A GP uses a chosen prior and a training data set to determine what the distribution or result should be like at a new test point. These graphs from Rasmussen and Williams give a simple example. Based on only the prior, we expect to observe a function that stays within the grey area of that top graph. When we add just two data points, we then restrict these functions to those that pass through those 2 points. So here and here. This then gives us a posterior distribution of function, which have the mean, which is represented by the solid black line, and the grey area, which then represents the uncertainty around the mean. And so in both cases, the dotted line or the solid lines in the top one just represent some random sample functions that are consistent with the known data. Once trained, the GP can provide the expected mean and standard deviation for any test point. GPs can be used in both classification and modelling or regression problems. When applying a GP, the user has to select a covariance function or kernel, which describes part of the relationship between the inputs and outputs. This covariance function is tuned using hyperparameters to best fit the training data. One common hyperparameter is a length scale, which describes the rate of change of the output and effectively limits how far each data point can affect the results. So this visualization website, I've put a link down the bottom there, it gives a good demonstration of this. If we take the same data and fit a linear covariance function, we get the image on the left. If we fit the radial basis function to this instead, having a look at the image in the middle, we get a very different posterior. It's also possible to combine several kernels for more complicated functions. So in the case on the right, it's a combination of linear and RBF, which gives us different properties again. So my data in this section is all from BIF-hosted iron ore deposits. So banded iron formation consists of layered iron bands interlaid with shale bands. In places, the BIF is locally enriched to form high-grade mineable ore. In the Pilbara, this ore is contained within two main BIF units, the Marramamba and Brockman iron ore formations. Data available in these deposits include downhole geophysical data such as natural gamma magnetic susceptibility, chemical assays, and measure while drilling data. The figure on the top right shows an idealized deposit diagram with the iron ore in here, located between shale at the top and unmineralized BIF down the bottom, with some weathered rock on the top of the deposit and a fault running through the center. And for anyone who isn't familiar with these types of open cut mines, they're massive. So these tiny trucks over here have tires that are a fair bit taller than me, just as a bit of a comparison. The first case I'm going to present is classifying natural gamma logs. The bedded shales within the BIF are highly consistent and generally used to define the lithological boundaries. The shales create peaks within the natural gamma logs, and therefore these logs are typically used to map out the boundaries within each deposit. In the Marramamba ore, the two most important shales are the AS1, AS2 bands here, which define the top of your ore, as well as your NS3, NS4 bands down here. Manual interpretation of these logs can be slow. It's prone to inconsistencies, particularly when it's performed by different people over a range of time. Results are hard to reproduce. So when training a GP, in this particular case, we use a library of signatures that contain both the desired output, which is desired signature, which is given an output of 1, and examples of other signatures, which are given an output of 0. So this is part of the library for an NS3 and NS4 signature. So you can see two positive examples on the left, as well as two examples on the right of other features which are negative in this particular case. The training libraries for this GP method were developed using an iterative process. The user would start by choosing a library of 6 to 8 signatures. The GP was then trained on these signatures and used to highlight signatures that were not adequately represented in the library. The user could then look at these signatures and choose those that should be included in the library. The GP was then retrained, and this was repeated until the improvements from the additional library examples decreased below a set threshold. Complete natural gamma logs were processed using a moving window. In this case, a window of 8 meters was used, but this varies according to the length of the example signatures in the library. A longer signature can be more distinctive, but means there is more log at the ends that cannot be classified. Therefore, the length of the signature needs to be changed based on the application and balance the amount of detail with the amount of log lost. For each comparison, the GP gives an output that describes how similar that particular section of library is to the desired signatures within the library itself. GP output consists of a mean and standard deviation. In this case, they are combined to label the log as containing the signature as not and as certain or not. Basically, if the range defined by one standard deviation from the mean remained on one side of the cutoff of 50%, it was considered certain. So examples of the 4 categories on the right. So the top left shows a certain signature here. The mean is well above the 50% cutoff, and even when including the standard deviation, is definitely well above that 50%, and that's a certain signature. Top right shows an uncertain signature. While the mean in the red line here does go above that 50%, when you include the standard deviation, it dips below the 50%, and it can't be confidently assigned to one class or the other. So similarly, the bottom ones show an uncertain no signature and a certain no signature. These images show the GP classification of several NS3 and NS4 signatures. A on the left is a typical example of the signature that is well classified. The other examples are all distorted or stretched in some way, which affects the classification, and they get worse from left to right. These tables show some results from classifying the AS1, AS2 signatures and the NS3 and NS4 signatures. The GP could confidently identify around 3/4 of the logs with a reasonably high accuracy. Looking at just the certain holes, all accuracies were over 92%. A lower accuracy is expected in the uncertain holes, which typically contain signatures that are distorted from faults or folds, or other shells and things that may show some similarities to the desired signature. To demonstrate why these boundaries are important, a GP was used to model the iron content of a section of the deposit. For those familiar with kriging, this GP was doing something very similar. When the entire area is modelled together, the ore and shale boundaries were ill-defined, and overall it was very poddy, and sections of known high-grade ore were labelled as waste. So you can see these pods here. Oh, this is actually a bedded shale that you'd expect to be consistent. And this is a known section of high-grade in here, which is unfortunately being classified as waste. Dividing the region into 3 areas based on those AS and NS shales I showed before gives this figure on the right. The top region still has a high variability due to the hard cap and alluvial sediments that are included up in this top region. However, this shale boundary here is starting to follow the boundary a bit better. The variability at the top causes the learning GP to decrease the region of influence of each data point. This effect is not seen when the GP learns only from the ore zone. In this region in the middle, the weight percent of iron varies gradually and consistently, and therefore each data point can affect a larger area. And this plot down here is just a highlight of this one in here. So there are some features that don't quite follow this boundary, but you can see they are forming a quite consistent, smooth transition on their own. Lowest area down here has issues with high uncertainty due to a lack of data. Generally, if you have a look down the holes, it's grading down into unmineralized BIF, which is expected. Not all boundaries are as distinctive as the shale boundaries I've been talking about. For example, the boundary between the alluvial sediment and bedded material at the top of the deposit creates a distinctive feature in the magnetic susceptibility, as well as in the aluminium and titanium assays. However, similar magnetic susceptibility features can occur at other places, typically high in the alluvial material or at the base of the hydrated zone. And similar assay features can also occur due to shales located in the material. Therefore, these need to be considered together to identify this particular boundary. To do this, two different GPs were trained. One GP was trained for the assays and another for the magnetic susceptibility. They were done separately due to the difference in data spacing. Geophysical logs down these holes are collected at 10 centimetre intervals, while the assays are only selected for 2 metre intervals. Other ways can be used to do this, but in this case, you did tend to lose a bit of that magnetic susceptibility feature by downgrading it to that 2 metre interval. For the assays, to make sure that both assays were used in the prediction, the ratio of the length scales was restricted, because otherwise sometimes it can make one assay by far the more dominant and the more controlling of the output. Once each GP was run, the mean and standard deviation were combined, with the assay GP given double the weight because it has 2 data inputs, and this gives a roughly equal weight to each of the 3. The highest combined output for each hole was selected as the boundary depth and labelled as certain or uncertain using the rules I discussed before. Magnetic susceptibility on its own only had an accuracy of 72% for the certain signatures, which would have resulted in a large negative impact on any surface modelled from the data. For the assays, the accuracy improved to 88%. And when they were combined, the GP had an accuracy of 94% in the certain signatures. This is high enough that data was considered suitable for boundary modelling. Both the assays and the combined method achieved acceptable values when they identified certain no signatures. However, the magnetic susceptibility had a much lower accuracy of only 75%. The combined method identified the fewest boundaries, but with the highest accuracy. The magnetic susceptibility GP was found to be overconfident, as it had the highest certainty of the 2 different GPs in the 3 methods, but the lowest accuracy. A while back, I showed how some stretched or distorted NS signatures were harder for the GP to identify. To improve in this area, a dynamic time warping covariance function was developed. So you can see the form of it there. It's based on the squared exponential covariance function, but the Euclidean distance was replaced by a pseudo distance dk, which is based on the warping factor and accumulated distance from the dynamic time warping algorithm. I won't go into detail here, but the main point is about those certain signatures highlighted in yellow. Where the GP, using a squared exponential covariance function, only identified 589 holes, the dynamic time warping algorithm identified over 1,200. However, the dynamic time warping doesn't provide a measure of uncertainty. Combining the 2 methods using the DTW covariance function allowed nearly as many signatures to be confidently identified, with a slightly higher accuracy than the dynamic time warping alone, as well as giving that measure of uncertainty that comes from the GP. Another type of data that I've classified using a GP is measure while drilling data. This data is collected on production drill holes while they are drilling the blast holes for each bench. They are more closely spaced than the exploration holes, however they have a higher noise level, and a number of pre-processing steps were required to clean the data before it could be used with the GP. As the MWD is less distinctive for each individual boundary, existing knowledge was used to restrict the data processed to that known to be close to the desired boundary. In this case, the data used was adjusted penetration rate, averaged to half-metre intervals and multiplied by 10,000 to resolve instability issues in the GP training. So this adjusted penetration rate is pretty much unique to this particular sort of application. So it's just the penetration rate, so how fast you're drilling down, divided by your force on bit and torque, and it basically accounts for the penetration rate, but including how much energy you're putting into the drilling to make it more consistent between different drilling modes and features. So these are some results. The coloured point lines in here, this is the APR from the drills, and these black points are where the GP identified a certain boundary. These points circled in red are where they've been incorrectly identified, where there's noise, and we know there's no correct boundaries over in this section. Generally, they're correct. So over here, you can see the higher APR, softer your material, the faster you're drilling, for the amount of effort you're putting in. And so most of these points do sit at the base of your softer material heading down into your harder ore. There's no ground truth available for these particular data, so it was difficult to measure the accuracy of individual points, and we generally did it by plots such as this, comparing it to things like the exploration holes or known geology from this particular area, if there was other information. Comparing the existing exploration hole-based surface with the GP surface created from the blast holes. So we've got this more straight, less detailed surface is your exploration hole-based surface, and this darker, more curved surface is based on the MWD data. So incorrect up in this area here, we've got incorrect MWD points, and they are curving it down where it's come back up straight here. Maybe not quite matching the exploration hole, but you expect it to be sort of similar up here, if more detailed. However, you see we've also got some incorrectly labelled points down in here, but because we did have these dominant correctly labelled points, they're not really impacting the GP. So this sort of method worked best where you had multiple benches above and below each other, and you can combine these to create an all-over surface. And just looking down here, you can see that where the original surface comes through straight, because it hasn't got any local data, you've actually got a little bit of a curve when you come through the MWD. So this is some more refined GP modelling done with some colleagues of mine. The high quality, sparse exploration data was combined with the noisier, more detailed MWD data. Due to the different data characteristics, covariance function was modified to have different levels of noise depending on the data type. As the mine is large, modelling the entire deposit together results in the overall trends dominating and local details being lost. To overcome this, the deposit was divided into smaller subregions, which were modelled independently, then stitched together. In the case shown to the right, when only using exploration data, there's an artefact here. So in this particular case, it was due to this actually some erosion happening here. And there is actually another hole under here, but because the top's been removed by erosion, you only get the below surface data, and it's caused a ballooning effect. Adding the MWD not only removed this feature, but it's also added some sort of finer details. It's a little bit hard to see here, but it's added some finer details to the surface. So moving along to the hydrological model selection. Groundwater systems being underground cannot be directly observed. Water balance models can be used to constrain overall inputs and outputs. However, in many cases, there are several competing models that can fit the overall water balance. And defining which is the correct model can be difficult. For these water balances, some components are well known and agreed on, while others tend to be more uncertain. In this particular case, we used the Lower Namoi as our test site, and as well as looking at how probable different inputs were, we investigated the impacts of the different magnitudes and different reported ranges of pumping values on how probable other components were in the model. So we used Bayesian model selection. So this is type of model selection where a prior probability for each possible component is updated to a posterior probability by evaluating model performance. In this particular case, we used a version proposed by Enemark, where we have a collection of hypotheses. Each hypothesis has a null hypothesis saying an uncertain component doesn't exist or impacts the aquifer, as well as the positive hypothesis that yes, it is having an impact. Initially, each has an equal probability, and then we come up with a final likelihood of each component based on water balance errors. So a series of models were designed that include every possible combination of the uncertain components. So the uncertain components are always included in the water balance, and then this set of models turns the uncertain components on and off to create this whole set. Multiple runs generate random values for each component and are used to create water balance. This is for each particular subpart of the model, each particular option. A metropolis Hastings sampling was then used to find the model with the smallest water balance error in each run. So then you run these quite a few times, and the number of times the specific model structure was identified basically indicates the posterior likelihood of these hypotheses being true. So just some NMark over on the right. If a particular component was contained in over 63% of the models, it was considered to have substantial evidence for it existing. If it was contained in less than 37% of the models, it was considered substantial evidence for it not existing. So these are our certain outputs for the model. Hydrologists are pretty confident that these ones exist. And most of these numbers are based on those reported by Barrett. However, the pumping values in yellow there were varied to include minimum and maximum of actual pumping values collected within those years, as well as the mean plus or minus standard deviation of those proper values, as well as the mean plus or minus half the standard deviation. And then the planned pumping values from Barrett were also used as a comparison. So these are our uncertain inputs, whether the water storage contained in the groundwater is being depleted, if we have additional lateral flow out, additional unreported pumping, additional flow back in from irrigation, additional flow in from the Grand Artesian Basin, and loss due to evapotranspiration. And that's the values that were calculated for each of those. So using the widest pumping range, which was using the actual values within these years, we had 15 to 110 gigalitres pumped per year. This was a huge range and resulted in no support for any hypothesis because the pumping range was multiple times the range of other components and essentially represented a really large uncertainty that just overshadowed everything else. Having a look at the conditional probabilities, it does show a few things that happened. So for these tables, it's a probability of the thing in the row existing if the column is true, and the probability of the thing in the row existing if the column is false for the bottom table. So M5 is Grand Artesian Basin, and there's additional support for Grand Artesian Basin if there's a decrease in the storage or there's additional pumping, and there's a few other things you can see there. Basically, these brighter numbers. These still aren't any sort of strong support, but you can see a few trends going on there. When we limit the range of pumping allowed, the uncertain components have a clearer impact on the modelling. There's still no substantial support for any individual component proposed here. There's some weak support for a decrease in storage. There's some support for evapotranspiration or additional pumping not existing in this case. This does split out and change a bit when you look at conditional probabilities. So, for example, there's substantial support for a decrease in storage if there's additional Grand Artesian Basin, no additional Grand Artesian Basin if there's irrigation in, no additional pumping in any of these cases, and no evapotranspiration in most cases. Further limiting the range of pumping, so now getting to only about a 30 gigalitre range here compared to the huge range we had at the start. Decrease in storage now has substantial support. It's definitely saying we're losing water from the storage there. There's substantial support for no evapotranspiration happening and no additional pumping. But having a look at this lateral flow out, there's still absolutely no support either way for anything happening here. I can't say if it's happening or not. And using the conditional probabilities, both additional Grand Artesian Basin and irrigation have substantial support in some cases, and there's still no evidence in any of these examples for or against the additional lateral flow out. Now, the reason for that, going back to the table at the start, is it's the smallest value. And even with this smaller range of pumping, it's just getting drowned out. It's just too small to make an impact. So our last one here looks at the planned or the allowed amount of pumping per year. So in this case, the components are much more dependent on which other components are included. Overall, there's only substantial support for no additional pumping, but the trends in general are similar to the previous cases. So if we look at additional probability, there's substantial support for decrease in storage in some cases, particularly if evaporation or additional pumping occur. But some components have substantial strong support in some cases, but not others. So if we have a look at, say, irrigation in, which is this one here, we're starting to get some support here, or even Great Artesian Basin in. Then we switch down to here and we've got support against. So in this case, it's quite dependent on which combination of components exist in the water balance model. So a really large range for pumping creates far too much uncertainty. There's no support for any cases and you can't really tell what's going on. Restricting the pumping range increases the support for some models and some components existing. And particularly increased support was observed for decrease in storage and against additional pumping or evapotranspiration. Using the predicted pumping values had quite a different impact compared to the actual pumping values because it changed the interaction of the components, making them more conditional than other components. However, whichever way you do it, if a component has too small a value compared to the other components, it's hard to get any support for it one way or the other. In conclusion, the values used in model selection need to be very carefully considered so they are realistic, but the scale between the different components is considered. We need to be careful in how these numbers are chosen and which components are considered certain. Some of these issues could potentially be addressed by modelling individual years, where values such as the known pumping could be very tightly constrained. And this may provide more information on different behaviours of the groundwater during wet and dry years.